think about what we took on here and we compare it to what IBM did with Deep Blue with chess. Chess was a fascinating problem to try to tackle, and one that many people felt, wow, this is associated with such a high degree of intelligence. But when you think about it, when you really break the problem down, chess is a finite, mathematically well-defined search space. There's a limited number of moves and states, and all the symbols are so completely grounded in those mathematical rules of the game. So while it was a great invention to be able to program that and scale it and figure out the evaluation functions and get the computer to be powerful enough to look far enough ahead to get good at this game and ultimately to beat Garry Kasparov, the problem was still almost more suited for a computer in some sense than for a human brain. Language is very different, right? Words by themselves have no meaning. They're only grounded in human cognition. The meaning comes from the context, the human experience that surrounds the use of that word. And so when we sit down there and we think, gee, how do we get a computer to understand and process natural language more effectively? We have a very different kind of challenge for a computer. When we started this, what was interesting about taking on this challenge and using it as a way to communicate to the broader public about computer technology and about artificial intelligence and what it really meant to do something like this, we sort of got this bipolar reaction. So on one end of the spectrum, we had people who thought, gee, what's really going on here? What's the big deal? But when you dug in, it was interesting that they really didn't understand what the challenge was about. And in fact, I did an interview once with a radio show host. It was a live interview. And the host started it by saying, so let me understand this. So you're taking all the Jeopardy questions and you're putting them into the computer, like into a table, and then you're putting all the answers in. And then when the clue shows up, the computer speaks the answer. Is that right? I'm like, no. We don't know what the questions are ahead of time. We don't know how to answer them. It's just completely open-ended. And the host said, well, wait a second. Well, then how do you do it? I said, exactly. So on one end of the spectrum, there are people who just didn't really sort of appreciate the challenge and thought it was sort of easy. And yet, on the other end of the spectrum, you had people who were like, oh my God, it's just frightening. As Skynet is here, and is Watson going to take over the world and enslave us all? So, of course, not true either. But we got that bipolar reaction. And part of what we had to do is, as we sort of knew that we were going so public with this challenge and with the technology that we ultimately built to take on the challenge, we had to do a bit of communication. And I started to talking about people about what do you think a computer is really good at? What does it find easy? What does it find hard? So here's some stuff that computers find easy. We'll see how you guys do. The natural log of 12,546,798 times pi squared divided by 34,567.46. Anybody? How about 50-50 chance? Greater than or less than 1? So there's got to be some smart people out there. Anybody? So it's less than 1. It's 0.00885. Computers are really good at this. Really, really fast at this. What else are they good at? Select the payment where the owner is David Jones and the type of product equals a laptop. So this is a pseudo-structured query language against a relational database. And we know that if we populate these big tables in computers, we can take queries like that, we can navigate them very rapidly over billions of rows, and we can find the information we're looking for very precisely. We can go from the owner to the serial number to the invoice to the payment, and we can do this really well. And the computer decides that David Jones is David Jones because the D is the D, because the D is represented by a number, and it's the same as the other number represented by the other D, and it's a very simple comparison. Of course, we can confuse the computer really easily by putting Dave Jones in instead of David Jones, and now, of course, you have to tell the computer all kinds of heuristics, that there are nicknames for some names, and things can get very complicated very quickly. So we don't do that, right? In databases, we give the computer, unique identifiers. So you give a serial number or a social security number so that we don't make that kind of confusion. And that's how we build an enormous number of applications that in many ways drive the economy. But when we deal with natural languages, it gets a lot harder for a computer. So here imagine that we have a question, where was X born? And if I had structured information, what I mean by structure is information that's organized in a table, and I programmed the computer to know that if I'm answering this question against that table, and I look up the person, assigned to the variable X, Einstein, and I look it up at the table, and I say, if you pull out the second column, the answer is Ohm, and this is the way a lot of people think things are done, then this sort of works. But imagine that I didn't tell the computer what this question meant, or how to answer it, or where to go to answer it. It just read a bunch of stuff. and it's trying to find an answer and build confidence in it. And it reads, one day from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. So somewhere in here is the birthplace of Einstein, is where Einstein was born, but you have to know a lot more. You have to pick out the people and the places, the relationships. You have to know the relationship between a birthplace and being born there. So with some confidence, maybe you can get Einstein was born in Ulm, but how about this one? X ran this. Now, of course, easy if I told you that you can answer that question by writing SQL against this particular structured table, and you can put in Jack Welch and get GE. But imagine instead if we had the computer just looking at that question, going off and trying to answer it. So if leadership is an art, then surely Jack Welch has proven himself a master painter during his tenure at GE. So what do you think the computer would come up with? With some confidence that Jack Welch was a painter at GE. Right, so dealing with natural language is it's very contextual. You're always using background knowledge to interpret and to infer and to produce confidence. So the uncertainty, dealing with uncertainty about the interpretation both of the question and of the content becomes a very, very important problem. Now, if Jeopardy comes along, for those of you who are familiar with the game, here's a game that has a broad range of topics, broad range of questions about all kinds of things expressed in a huge variety of different ways. We have some examples. If you're standing, it's the direction you should look to check out your wainscoting. Anybody know interior design people here? So you look down to see your wainscoting. But you look at that and you say, oh gee, I know how to solve Jeopardy problems. I'm going to model every possible direction, right? So north, south, east, west. How about I just do all the degrees around a compass? Well, how about up, down, right, left? Those are those other kinds of directions. Well, there's another Jeopardy question that says this is the direction of fabric, etc., etc. And the answer is grain. Would you have thought to represent grain as a direction? So one of the challenges here is the breadth of domain that Jeopardy deals with, both in terms of language and how it's used, its usage, but also in terms of just topic. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid cushioning the nucleus. Anybody? Cytoplasm is the answer. Of the 4 countries in the world that the U.S. does not have diplomatic relations with, the one that's farthest north. Answer is North Korea. So broad, open domain, complex language, you have to have very high precision to compete with champions at this game. I'm going to show you a graph in a minute. And you also have to have very accurate confidence. And this is a very interesting aspect of the Jeopardy challenge. You have to know what you know. Because in the game, if you buzz in and you say, I want the first chance to answer that question, and you get it wrong, you lose the dollar value associated with that question. So there's a risk associated with answering a question and getting it wrong. So you have to produce your answers, and you have to produce confidence, a probability that you believe that answer is correct. And what does that imply? It implies that you're collecting and you're evaluating evidence, textual evidence that supports or refutes those possible answers. And you have to do this very, very quickly to compete at Jeopardy, and I'll talk about how quick in a second. Just to give you a sense of that broad domain, we looked at about 20,000 randomly sampled Jeopardy questions, and we plotted the thing that we referred to, like this person or this organization or this month or this light or this whatever. And there's a long, long tail phenomenon. First of all, 13% of the questions don't refer to anything. They say it or this. But the other 87% get you very long tail. Even if you attacked the head of the tail and tried to model everything you knew about it, you'd only cover about 10% of the data, which isn't going to get you anywhere near competing on Jeopardy. So you have a wide range of things: vegetables, months, insects, diseases, countries, signs, vegetables, all sorts of things are referred to in the Jeopardy domain, and working on any one of them is going to cover very little bits of the data. So you have to really try to use natural language processing technology to analyze, large volumes of as-is text, to try to understand statistically how words are used in different contexts, how they might be classified, and whether or not that text really answers that question. And you have to do that over as-is content. Lincoln blogs. Treasury Secretary Chase just submitted this to me for the 3rd time. Guess what, pal? This time I'm accepting it. Anybody? Resignation. So, it's an interesting answer. Resignation is right, and you may or may not know the historical fact, but even if you don't know the historical fact, what humans will do here is come up with plausible guesses. They'll use the context. They'll use what kinds of things do you submit? And if you're a Secretary of the Treasury and we're talking about a president, what kinds of things are even worth talking about that you submitted? and you use that context to create a plausible guess like resignation. Well, I was giving this, one of the team members was giving this talk to a sixth grader, and we asked, what do you think? What do you think the answer is? And the sixth grade came back and said, friend request? So they didn't know the historical fact, but again, they used the context and their experience with language to come up with what they believed was plausible. And for them, that was plausible. So one of the things we had to do was acquire knowledge about how language is used, a combination of syntax and semantics. And we had to do this automatically because we couldn't sit there and we didn't handcraft databases to address the Jeopardy domain. It was too broad and too varied. So we wrote programs, natural language programs, parsers and information extractors and relationship extractors, and we'd go out and we'd analyze large volumes of text. We'd build what we call syntactic frames, subject, object, verb, prepositional phrase, object with a preposition, and so forth. And then from there, we build semantic frames. So and then we computed statistics over that. So we'd be able to learn, for example, inventors' patent inventions, officials submit resignations with some degree of certainty. People earn degrees. Where? At schools. Right? Because you can ask, well, where did so-and-so get their degree? And you can answer with a city or a state. When the real expectation is the right answer is a school. How would you know that? You know that because this is how people use language. So we analyze this to learn this. A fluid is a liquid. Liquid is a fluid. Which one's actually correct? If you looked up a strict physics taxonomy, fluid is the more general concept. Liquid is a type of fluid. Fluid is not a type of liquid. Vessels sink. But people sink 8 balls in the game of pool. So we extract this information automatically, and we build large knowledge bases that contribute to how we answer and score questions. So now we have that question again. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid, cushioning the nucleus. And what Watson does is it looks at that sentence, that question, it analyzes it in many different ways. It does a syntactic parse. It looks for semantic information. It looks for different phrases and terms and weights them, and generates many queries. From those queries, it searches mostly unstructured content, but also it uses databases to help classify and interpret things. And it comes back with lots and lots of different answers, what we call hypotheses. So organelle, bathroom, cytoplasm, plasma, mitochondria, blood, and the list goes on. And then it looks at that content, the information that it gathered that support these answers, and it tries to analyze them along different dimensions of evidence, what we call dimensions of evidence. One, of course, is classification. If you have cytoplasm as one, and you're considering cytoplasm as one of the possible answers, one of the candidates, you want to know to what degree do you believe cytoplasm can be considered a liquid? Well, so based on what I showed you earlier, it's reading all this content and finds a passage cytoplasm as a fluid surrounding the nucleus. So now, in order to score this as supporting cytoplasm as the answer, Watson generates an intermediate hypothesis as well as a fluid, a type of liquid. Now, unfortunately, it can't ask the host or the other contestants in the game, so it generates that and tries to prove that by looking at unstructured content, using all the algorithms it has, looking at folksonomies and taxonomies and whatever else the algorithms can get their hands on. And WordNet, which is a strict taxonomy, says, you know what, I've got nothing for you, because it knows that a liquid is a type of fluid, but not the other way around. But that mine data is associated with other algorithms, and it says, you know what, fluid can be considered a liquid. And because we use statistical machine learning to train over the Jeopardy questions, we learn we can trust that learned content for answering Jeopardy questions. If Watson trained over physics tests, it would give that strict taxonomy represented by WordNet much more weight than would that information mined by more natural language content. But here in Jeopardy, that was able to give weight that it's reasonable to believe in this context that liquid is a type of fluid which allows me to boost cytoplasm, boost the confidence in cytoplasm. So what I just gave you a sense of is how, sort of a little foreshadowing of how Watson really works to answer these kinds of questions. A long tiresome speech delivered by a frothy pie topic. Anybody? So, you know, it's hard to argue with the IBM executives that this is an important business problem to solve here, or important business question to answer. But, you know, when you look beyond the question and you look at the technology required to answer it, in fact, you have to break the question down. And this became one of the things we had to do in Watson is decompose language, both on the question side and on the content side. Break the question down into different parts, solve those parts independently, In this particular case, the category was edible rhyme time, which implied that two pieces would have to rhyme. So you constrain that, you get harangue and meringue, and then because it's English, you'd put the thing, the modifier before the thing being modified, and you get meringue, harangue. And Watson does exactly this kind of thing, not because we want to build an expert in making pies, but because we wanted to be able to advance the field of natural language processing, and learning how to decompose language, questions, and content into their subparts is an important part of that problem. Shirts, TV, remote controls, and telephones. This is a Jeopardy question. Anybody know the answer? Buttons. I think I heard buttons. I was thinking things under my couch. But that's right, buttons is right. And if you think about the kind of algorithm to attack a problem like this, is you're starting with these initial entities and you're looking for all the things they have in common. Well, it turns out, of course, a computer is not a human, doesn't experience this thing like humans does, and finds all kinds of things that are in common, like plastics and oils and things made by man. Why buttons? So there's a human bias, of course, and as you would expect. Human language is created by humans to communicate with humans about their experience, which creates a bigger challenge for computers. On hearing of the discovery of George Mallory's body, he told reporters he thinks he was first. So I put this on the same slide called the missing link slide, because what's going on here, you can see obviously the first one, you're looking for that common link, but it's not so obvious in this one. It turns out, of course, to answer this question, you have to figure out that George Mallory is associated with Mount Everest. Mount Everest, however, is not the answer to the question. It's one of many things associated with Mount Everest that you can be first at. So the answer is actually the person who was first at Mount Everest, Edmund Hillary. So one of the challenges for the computer is to look for those opaque references, find them and score them, and find the connection to the other parts of the clue. So lots of deep analysis on unstructured content to make this work. I'm going to skip this slide. I want to talk a little bit about now what the competition was. I give you a sense of what, the kinds of questions you get asked by Jeopardy in the Jeopardy contest. I give a foreshadowed a little bit of how Watson tries to solve the problem. But let's talk about what Watson was up against when it had to go play against Ken Jennings and Brad Rutter in that now famous game on television. Here we graph the actual performance of humans on historical Jeopardy games. So every dot on this graph is an historical Jeopardy game, and what I'm plotting is the performance of the winner of that game. And along the x-axis, I'm plotting the number of questions the winner was fast enough and confident enough to buzz in and get to answer first. So I have two competitors. If I'm confident enough that I know the answer and fast enough, I buzz in and I get a chance to answer that question. And the winning player, on average, answers nearly 50%, about 47% of the questions, meaning they're getting a lot more of their share on average. And their precision, the y-axis, is how many of those questions they got to answer they actually got right. And it's between 85 and 95% if you look at the center of that green cloud. That's remarkably high performance. The red cloud are Ken Jennings games. Ken Jennings played 74 games. He won 74 games in a row. And when you look at his cloud, and he acquired, on average, 62% of the board, meaning he buzzed in first and got a chance to answer before his competitors. 62% of a game, on average. So, sometimes 70 and up to 81%. So you can only speculate that the way he did this was he just assumed he knew all things. And unfortunately for his competitors, he was right. Had about a 92% precision on the questions he answered on average. But you see the cloud is widely distributed. Along that brown curve is a state-of-the-art question answering system been developed at IBM. We had several partners over several years working on this, had many of the state-of-the-art techniques, and we turned it on to play Jeopardy, to test it on Jeopardy questions. We did some adaptation to adapt to the style of the Jeopardy question, and we tried it, and it got that brown curve. And what that brown curve says, so we call it confidence curve, and what it says is on about 5% of the data that it was most confident in, it did about 47% precision. As it had to answer more and more questions, its confidence diminished, went down, and its precision went down, plateauing at about 15%. This, of course, left a huge gap between where the state-of-the-art was performing and where we had to be to compete with Jeopardy champions. So why would you even take this on? So the compulsion to innovate. A few things, and I hope and I imagine that this should resonate with the entrepreneurial community. First of all, I think when I reflect back on why I was compelled to do this, part of me had this irresistible vision, which is, and what I mean by that is a vision of the future that you just know in your gut someday must happen. And when I think about how humans interact with computers, I think that, we have to reach that point. There's no way there's a future where humans are not fluently dialoguing with computers in natural language. Whether or not we think of computers as humans, that's a whole other story. Is it doing this like a human brain would? I'm agnostic about that. But can I imagine a future where computers aren't doing a better job at understanding my natural, what I'm saying, and moreover, understanding all the things that humans are writing about and communicating with each other? They have to get better at that. It was an irresistible vision. It must be so. Don't know exactly when, but it must be so. And it's hard to resist. Ultimately, for me, for someone in my background, and for the team that I represented at IBM, impossible to resist. The other piece you have to have is a bit of wisdom. And the bit of wisdom tells you, you know what? It can be now. There's reason to believe that we can start to do this now, that we can make huge progress against this vision now. So you have to have enough knowledge, enough experience to imagine realistic possibilities. And the Jeopardy challenge to me, based on our experience with natural language understanding, with question answering, with artificial intelligence, there was reason to believe that this Jeopardy challenge can be taken on and we can advance this in ways we couldn't have before. There was huge advances in machine learning, huge access to large amounts of data that you can do statistics on. There has been decades of research into natural language parsing. If we can figure out how to pull all this stuff together and advance it against this goal, we can break new ground. So there was wisdom behind it to believe this is possible. And of course, the last point is you have to have a lot of mettle. You have to believe it could be you. Or in this case, it will be us. We can do this. So irresistible vision, a bit of wisdom, to believe that it can be done now, and the belief that, you could stand out of the crowd and you can do it. And you have to have that willingness to challenge the status quo. And in fact, we met this, at IBM, there was a big internal debate about whether or not we should take something on, especially with this kind of public exposure. There are many who believed that this was impossible to do. We'd fall on our faces, it would be folly. But in the end, the debate raged on, and IBM decided, this is what IBM research is all about. Taking risks like this is what we're about. Pushing the technology is what we're about. Capturing the imagination, and we're going to take this risk, and the research project was supported. A few guiding principles, going back to that bit of wisdom. We had to put a stake in the ground. We have to say, we're going to approach this in a certain way. We're not going to try to hand code big giant databases. That's not a useful approach to this. It's not going to work, number one. Number two, it's not going to scale to new problems. So large handcrafted semantic models or databases or ontologies aren't going to conquer the problem. We were going to take that approach. We would use existing ontologies, many of them, to integrate with natural language processing, but we weren't going to attempt this by curating data. Intelligence for many shallow methods. Another stake in the ground, we said. There's no one algorithm that solves a natural language processing problem. There's no simple algorithm that answers all questions. There's no maximal equations for QA. But rather, this is going to work if we make many, many diverse algorithms, and we figure out how to integrate them and combine them, and we figure out how to manage or balance their contributions, their relative contributions. And we did this, of course, with statistical machine learning. And finally, that massive parallelism was going to be a key enabler. That a large amount of compute resources were going to be necessary to have the computer pursue many different hypotheses, gathering and scoring evidence. And the idea was the one that gathered the most evidence and scored the highest, based on many different competing hypotheses and competing algorithms, or complementary algorithms, potentially overlapping algorithms, we would be able to find the best answer, but that would require massive parallelism. This is what we came up with, DeepQA. So this is from 50,000 feet high. What does the architecture look like? Analyzes the question and the topic, decomposes it into different parts. For given multiple interpretations of the question, hundreds of sources, hundreds of possible answers, we go out and look for different evidence now. So we get many independently competing hypotheses, independent threads flowing through the system, each one collecting bits of evidence. Now we have tens of thousands answer evidence pairs. For each evidence answer pair, we have a whole ensemble of algorithms, many of them developed independently, that score that evidence from different dimensions, from temporal information, spatial information, looking at syntactic structure, semantic structure, logical structure, and scoring them, looking at modalities, looking at negation, looking at all kinds of things to come up with scores, all working independently to allow that massive parallelism. So the algorithm is ultimately embarrassingly parallel, and we intended to do that, knew that we would have to exploit that to get this to be fast enough. In the end, you end up with a ranked list of answers, and each one has a confidence. If the top answer's confidence was above a threshold, the computer believed that it knew the answer with enough probability to take a chance and bet, take a chance and buzz in to answer that question. That threshold would change during the game. So if Watson was way ahead, it would make the threshold higher. So why take a risk? I'm way ahead, so now I want to be 95% sure before I buzz in. If it was way behind, it would lower that threshold and say I need to catch up. If I'm even only 40% sure, I'll take a risk. So that threshold will change during the game. Here's the stack to give you a sense of how we built this from IBM Power 7 hardware. On top of that, Linux. On top of that, UEMA-AS. UEMA is the unstructured information management architecture embedded on asynchronous messaging, which IBM spearheaded, created at IBM, and now contributed to open source. It's now an Apache open source project. On top of that, we built a statistical learning framework, and on top of that, many, many different algorithms, statistical and rule-based analysis algorithms that we plugged in to the different parts of that architecture. To analyze questions, collect content, and ultimately analyze and score the content. Hundreds of algorithms were developed over the 4 years populating that architecture. And over those 4 years, we were able to progress from that initial baseline all the way up to, you see that top line, actually that was the last large measurement taken on 200 games worth of blind data. Neither the computer nor the developers ever looked at this data, and you'll see it slicing right through the winner's cloud, meaning that if you look at about 70% answered, it's doing between 87 and 90% precision on those questions. So this means this, at this level of performance, would it win every game against the competitor? No, but it would clearly be competitive against champion players. Watson is actually a bit better than that now, but that was the performance that we played those games with. So it took 2 hours to answer a single question on a single 2.6 GHz CPU, which the Jeopardy producers kept arguing with me that would make a very, very boring game. So we had to scale that computation out, and we did on over about 2,880 Power 7 cores, and we got that computation again, because the algorithm was embarrassingly parallel, we were able to scale it up very effectively, again using UEMA-AS, and we delivered on average about 3 seconds, answering a question on average about 3 seconds. Now, the distribution went out to maybe 8 seconds on some questions answering in 2, but we averaged out around 3 seconds, which was competitive enough to play the game. Now, I just want to give you, a sense of things here. So in spite of the architecture, and over those 4 years, we had a whole methodology for creating and integrating and measuring the value of different algorithmic approaches to different dimensions of the problem. Watson wasn't always that good, and I wanted to give you a sense of some of the growing pains we went through to help you appreciate the challenge and the feelings that you can imagine the team went through as we were going through these early phases. So here's a Jeopardy question. The American Dream. Decades before Lincoln, Daniel Webster spoke of government made for, made by, and answerable to them. Anybody? People. Watson? No one. So actual Watson answer from the early days, but you're right, the answer was the people. How about this one? New York Times headlines. An exclamation point was warranted for the end of this in 1918. World War I. I think I heard World War I, that's right. Watson? A sentence. That's not entirely wrong, right? So obviously you can see where some of the evidence for that came from. How about this one? Let's see. Milestones. In 1994, 25 years after this event, one participant said, for one crowning moment, we were creatures of the cosmic ocean. This is the Apollo moon landing. Watson? The Big Bang. Of course, there weren't a lot of people around to comment on the Big Bang, but But once again, you can start to see where that comes from. How about this one? The Queen's English. Give a bird a tinkle when you get it to town and you've done this. Call on the phone, Watson? And the answer to this one is very, very hard to explain, but I just put it up there because it always makes me laugh every time I do. This is a very early version of Watson. Fatherly nicknames. This freshman was the father of bacteriology. I heard Pasteur, that's right. Watson? So it was really important for the engineering to facilitate the science here. The way we conducted ourselves was once we sort of put a stake in the ground about how we were going to technically approach this and built that architecture, it was really about developing algorithms that got better and better at both understanding questions and scoring content, basically analyzing the natural language and coming up with meaningful scores, looking at the data from many different dimensions. And we were very, very goal-oriented and very, very disciplined in this. We had our end-to-end metric, which we looked at. Remember that graph? We looked at, precision and confidence. Precision, confidence, and ultimately speed. But when we looked at the algorithm development, it was precision and confidence. And in parallel, we would take those algorithms and we would scale them out, and we would look for bottlenecks. If we found bottlenecks, we'd come back to the algorithm designers, and they'd have to make those. They'd have to solve those software problems. But in the meantime, in parallel, we were scaling the system out. On the algorithm development, though, we had to understand what algorithms were going to matter. How do we have to make them better to win this? And individual researchers would come up with ideas, and they would have to do headroom analysis. They'd have to come up and they'd have to argue by looking at the data that this idea, in the best case possible, would have this kind of impact on the system. And we make incremental investment in that idea. At some point, if that idea wasn't panning out, we would cut that off and we shift resources to another idea that looked more fruitful and was making progress faster. And we iterated over this regularly. We put everyone in the core team into one room to maximize bandwidth of communication, to make sure everyone felt they were in this together. And this had a big impact on how quickly we were able to work on this. In fact, over the 4 years, we performed over 8,000 documented experiments. Every one was entered into the system in a big integration run. The runs would produce 10 to 20 gigabytes of the error analysis data that we loaded up into DB2 databases. Then we had web-based tools to slice and dice that data so that we can investigate why didn't it work, what went wrong, how do we make these algorithms smarter. And we continue to iterate on that, working toward that end-to-end metric. How well can we really play Jeopardy? The precision, the confidence, and the speed. Just to understand what was going on, we had to build tools. Here you have a question, and you see all the answers along the left, Argentina and Bolivia being the top two answers to the question. It's a bit chilly today. Chile shares as long as land border with this country. And you see actually hundreds of features that were produced. And we can actually plug in the different models and see very quickly which features were contributing more or less to the right and wrong answers. So it would help us zoom in on which algorithms were potentially causing problems as they independently scored the various answers and their evidence. So we had to create tools that actually help us even see what was going on as we independently created these features. It was a very important way to innovate, because if everyone had to build, we always had to build and iterate consensus on a single data model of the world or a single way to score things, we'd be stuck. We'd still be in meetings. But rather, we enabled, the methodology we used enabled people to create these algorithms independently, but then we needed tools to help us understand how they were interacting. And these kinds of tools helped us do that. And from those tools emerged a very, very important concept, which we called an evidence profile. And this ends up speaking to how we move forward with Watson. Here we have that clue: Chile shares its longest land border with this country. Now, don't forget, Watson doesn't look at this and say, gee, I know how to answer questions like this. I just look up the borders and I look up the lengths and I find the longest. We're solving this from looking at natural language content. We have some geographical databases that help us with location information, But for the vast majority of these things, we're trying to analyze what documents say about the question. So we get those features got aggregated up into location features, passage support features, popularity features, source reliability features, classification features, and there are many other categories as well. And then given the machine learning models, they would weigh the score. And you see that Argentina won in location and passage support. It lost in popularity because there was more content talking about Bolivia and Chile being in a land dispute over a border dispute. Source reliability, maybe a lot of that stuff was coming from blogs. Watson learned that the sources that were contributing more to Argentina were actually more reliable based on training data, and luckily classified in both those countries. You'll find Bethel College and Seminary in this holy Minnesota city. Turns out there's a St. Paul, Minnesota, and a South Bend, Indiana, that both have, unfortunately for the computer, a Bethel College and Seminary. So these answers end up competing, and you'll see that Watson likes St. Paul, Minnesota because of the location information, which it should, because after all, it's in Minnesota. But South Bend went out in all these other categories, and here we do error analysis and we say, you know what, a question like this, location information should get weighed a lot higher and overwhelm those other scores. So this taught us something, how to create a new class of question and how to better train to weigh different dimensions of evidence differently for different kinds of questions, ultimately creating many different models in the system. Now, of course, you could look at this and say, wait a second. You know, holy, there's a pun going on here, which helps you distinguish the right answer. And what this technique allowed us to do was to actually have someone create an independent pun detector, plug that in, train. That pun detector actually earned weight and put St. Paul over South Bend. But of course, what happened was Holy Cross, Minnesota ended up being in second place because after all, Holy Cross is more holy than St. Paul. So deep analytics, speed, and gave us really, really impressive results. Not only did we win that game, but there's a lot of variability in Jeopardy, as you may know, because of the daily doubles and the Final Jeopardy and the betting and so forth. And we played 55 real-time sparring games against tournament and champion winners, and won over 70% of those games. So Watson was consistently performed at a champion level in spite of the variability of the game. You know, what was interesting, too, was that in order to get this project going and for us to focus on this, we had to build an integrated system against a single end-to-end metric. And one of the challenges, we had as a team working in a research environment like this is everyone has incentives. They're conditioned to sort of do their research kind of in silos. I'm going to build a parser, and I'm going to get credit or write papers because it performs on a parsing metric. I'm going to write a named entity detector, a relationship detector, and I'm going to get credit because it performs on the standard data evaluations for that particular component. But what happened with Jeopardy was we couldn't afford to do that, because the truth of the matter is all these different components, when you put them together into a single system, they overlap. Some cheaper techniques, might eat the lunch of a much more complicated technique. You might not put that in a research paper. But when you're building an end-to-end system, you can't afford not to understand and appreciate that. The good news is that when we were done with Watson for Jeopardy, and we went back and we looked at all those component algorithms and we tested them against those individual metrics, we were leaders in every single one, from parsing to disambiguation to entity and relation detection to passage match, text and tailwind, which is incredibly gratifying for us as researchers, but also for how we approach the problem organizationally. How many people actually saw the Jeopardy game? Enough people to care about what happened with Toronto? So there was a Jeopardy question. I'll skip to it. It was the category is U.S. cities. The question was, its largest airport is named for a World War II hero. Its second largest for a World War II battle. And it was a Final Jeopardy question where you have to answer. You don't have a choice. You don't buzz in. And you'll see Watson's answer panel there. Toronto was the ¡1 answer, but with only 14%. On a normal question, Watson would have never even buzzed in for that. But because it was Final Jeopardy, he had to reveal its answer. And of course, the comment was, my gosh, Toronto isn't even a U.S. city. How could you, Watson? So it turns out, of course, Watson learned that in Jeopardy, categories don't mean as much as you might think they mean. Here are actually Jeopardy questions. U.S. city, the answer is shuffleboard. The Erie Canal. Country clubs, the answer is a mace, a baton. Another one in that category is the League of Nations. Authors, the answer is the Book of Job in Romania. Just because a category title names a type of entity doesn't mean the answer to the Jeopardy questions is of that type. So Watson learned that. So the fact that the categories be a U.S. city gave Watson very low signal that the answer needed to be a U.S. city. Moreover, when Watson looks at an answer, like for example, Toronto or Chicago, it says, you know what, being a U.S. city would be good here, but it's not going to make or break this because the category doesn't always mean that. And Watson was right about that. Now, when he asked Watson, is Toronto a U.S. city, he says, well, you know what, I have more evidence that Chicago's a U.S. city, but because I have to be very flexible with language, remember, grain is a type of direction, right? I have to be very, a fluid is a type of liquid. Very flexible with language, goes out and says, well, what do I know about Toronto? Toronto has an American Baseball League. Toronto was talked about as an American-like city. So there's a weak signal that one might consider Toronto a U.S. city. And that technique gave us tremendous power in Jeopardy. And this one makes you look stupid, but in general gave us tremendous power. So we still like Chicago from that perspective, but we weren't weighing U.S. city very much. On the World War II side, we found Lester Pearson Airport in Toronto associated with World War II. We couldn't get enough confident evidence for Chicago in that way, and Toronto edged out Chicago. But still, Watson knew it really didn't know the best answer here. If you change the question and you put this U.S. city's largest airport, then Watson has a much stronger signal that you're looking for a U.S. city, and it put Chicago in first place, of course, with higher confidence. But of course, the game didn't go that way. But the notion of coming up with evidence profiles and producing the evidence that supports or refutes an answer is a very, very powerful notion. And we think this could get applied in healthcare, life sciences, and tech support, enterprise knowledge management, and government, in many areas where you need to be more precise over natural language content. Imagine in medicine, where the evidence profile the dimensions become symptoms, family history, personal history, medications, and findings. And all that evidence is coming from a combination of structured and unstructured content. You can imagine a scenario where all this information from symptoms to journals to papers to notes and hypotheses and blogs are feeding into Watson, which is helping to produce an evidence of differential diagnosis, providing sort of a portal where the doctor and or patient or other people involved in supporting and caring for a patient can look and see how that evidence evolves in support of either different diagnoses or even different treatment options, giving them immediate access to the evidence that supports those answers across these different dimensions. It's a very, very powerful notion, one that we are very excited about moving forward. If you think about what it means to build on Watson, you can imagine different APIs. A question answering API where you might input initial questions. Watson can produce answers, confidences, evidence profiles like we just saw. But it also can produce follow-up questions. Jeopardy was very artificial in the sense that you gave your answer, you couldn't dialogue. You couldn't say, well, wait a second, you're really looking for a U.S. city here? You couldn't say that. Right, but in a real scenario, you can dialogue. You can ask those follow-up questions. If you consider cytoplasm a type of fluid, then a type of liquid, then that's probably your answer here. So that kind of follow-up question and dialogue can occur. We also imagine a teaching Watson API where in addition, giving the user the topic information, Watson knows when it sees right answers, it can figure out why it failed. And it can say, you know what, I might have failed here because I didn't realize that if you demonstrated something, you might have produced it. Or if you invented something, if you got a patent, you might have been a developer on the invention behind that patent. So it can actually ask questions to humans to help fill in its holes that would make it smarter in processing natural language going forward. So this is another API that you could engage in different ways. So very excited about that as well. There's a large team behind me representing people who are experts in a wide range of areas, from computational linguistics to machine learning to AI. We focused on the core algorithms, on the speed, on speech. The significant part of the investment, of course, was in the core algorithms. A number of university collaborators as well, and I just want to thank them all. Thank you.